The aperture refers to the circular opening of the lens diaphragm, which allows us to control the amount of light coming into the camera. We said that the ISO numbers and shutter speeds always double or halve, depending on which way along the scale you are moving. Apertures work in the same way. Each time you move up or down the aperture scale, the amount of light getting into the camera is either doubled or halved. This is the aperture scale found on modern cameras: f1, f1.4, f2, f2.8, f4, f5.6, f8, etc. This expression f1 or f1.4 is a shorthand expression for saying that the diameter of the aperture is equal to the focal length f divided by 1, or focal length divided by 1.4 divided by 2 divided by 2.8, and so on. If we take a 50mm lens as an example, this would mean that our apertures have the following diameters. So 50mm divided by 1 equals 50mm. 50mm divided by 1.4 equals 35.7mm. 50mm divided by 2 equals 25mm, etc. If we know the diameter, we can also calculate the area of each aperture. To calculate an area of a circle, in geometry we use the formula A equals pi times r squared. Remember that radius equals half the diameter. If you take the focal length of a lens and divide it by each of the numbers in the aperture scale sequence, so 1, 1.4, 2, 2.8, 4, etc., you will get diameters for circles where the area of each circle in the sequence is half the area of the circle that precedes it. Once again, if we move from the left to the right, the circles are halving in size. If we move from the right to the left, the circles are doubling in size. Thus, by varying the aperture size, we are either halving or doubling the amount of light that gets into the camera. When we looked at the ISOs and shutter speeds, it was easy to see that the numbers are either halving or doubling. So why is the aperture scale ordered differently? Why do we use these numbers? This is because when it comes to apertures, we are dealing with circles. If we go back to the formula, A equals pi times r squared, we could rearrange it to say that r equals square root of A divided by pi. Now, if we want to calculate the radius for a circle half the size, if you look at the smaller circle and exchange A for A divided by 2, or half the area, another way of writing this would be to say that r2, or radius 2, equals square root of A times pi divided by the square root of 2. Notice that the numerator, the top part, equals the radius of the previous circle, so we could say that the radius 2 equals the radius 1 divided by the square root of 2. And then we can repeat this a number of times to get a sequence of circles where each circle in the series is exactly half the area of the one preceding it. This way we end up with the geometric sequence of the powers of the square root of 2, which, if simplified, can also be written as 1, 1.414, 2, 2.828, 4, 5.656, 8, 11.135, etc. And which, for the sake of convenience, can again be rounded off to 1, 1.4, 2, 2.8, 4, 5.68, and so on. This halving or doubling of light in photography is commonly referred to as a stop. If we change the lens aperture from f2 to 2.8, we would say that we close the lens by one stop. If we change the shutter speed from 1/60th of a second to 1/250th of a second, we would say that the shutter speed is 2 stops faster. By varying the size of the aperture, we control the amount of light getting into the camera, but this also affects the way our images are rendered visually. The depth of field refers to the area of sharp focus in an image. In other words, if you focus on a subject, how much of the field in front and behind the subject is going to be acceptably sharp. A wide aperture like f4 will give us a shallow depth of field. Shallow depth of field is often used in portraiture to isolate the subject from the background. A small aperture like f11 will give us a deep depth of field. Deep depth of field is often used in landscape or architectural photography to keep the entire scene in focus. Let's see what happens if we shoot the same scene using different apertures. As you can see, as we start using progressively smaller apertures, the depth of field increases. With the lens fully open, the background is blurry. As we close the aperture, the background comes more and more into focus. However, the amount of light entering the camera for each image remains the same, because each time we change the aperture, we also change the shutter speed. This way, the total amount of light entering the camera remains the same, even though we are using a different combination of aperture and shutter speed. The depth of field changes with aperture, but it is also dependent on the focusing distance and focal length. For any given aperture, the farther the focusing distance, the deeper the depth of field. For example, if we are using a 50mm lens set to f5.6, focused at 1 meter, our depth of field is going to be only 13 centimeters deep. If we change the focusing distance to 3 meters, the depth of field increases to 1.25 meters deep. If we focus even further to 10 meters, the depth of field goes up to 24.84 meters. As we see, the depth of field varies with distance. It also varies with the focal length. For any given aperture and focusing distance, the wider the focal length, the deeper the depth of field. We said that if we use a 50mm lens, set it to f5.6 and focus at 3 meter distance, the depth of field will be 1.25 meters deep. If we change the focal length, for example by zooming out to 24mm, the depth of field will now be 22.75 meters deep. So to put this into practice, if we want to have a really shallow depth of field, if we are shooting a portrait for example, we would easily achieve this by using a long lens, wide aperture and a close focusing distance. If we want to have a really deep depth of field because we are shooting a landscape, we would probably want to use a wide angle lens, small aperture and a medium focusing distance.